In this video, we will introduce electric potential, which is also sometimes called voltage, which is in fact an easier name to remember because it's less likely to be confused with potential energy. We will also look at equipotentials and the relationship between equipotentials and field lines. We start with the concept that we have just learned, the potential energy of two-point charges. We define this relationship between potential energy and potential. So potential energy is U, potential is V. That's easier to remember because potential is measured in volts. Notice that what we have done is, instead of treating the two charges in the system equally, we are separating them into a test charge little q and a source charge big Q. Comparing these two relations, we arrive at this expression for the potential created by a source charge. Let us note a few properties of the potential. First of all, it is a scalar. It only depends on the Q of the source charge and the distance between the source charge and the point at which you want to find the potential. Notice that since K and R are both positive, the sign of V only depends on Q. So to create a positive potential, you must have a positive charge. To create a negative potential, you must have a negative charge. So if you have two positive charges, there is no way that their potentials will cancel out in any way. They can only add up. And finally, notice that as the distance goes to infinity, the potential goes to zero. This is in fact a choice that we have made. It turns out that we never actually measure potential directly. We always measure potential difference. And so it is convention to set the potential at infinity to be zero to provide a simple reference point. Let us look at this example question. In case A, we have a uniformly charged ring of radius r, and in case B, we have just a point charge. Both have the same amount of charge, and both have a distance r from a point P, in which case is the electric potential at P higher. Pause the video and think about this yourself for a moment. We now discuss the answer. The answer is the potential at P is the same in both cases. They tie. The reason being, the amount of charge is the same, and all that charge is at a distance r from the point P. Even if it's spread out in a ring form, every little piece of the ring is at a distance r from the point P. And so they all create the same potential, and since potential is a scalar and not a vector, they don't cancel out, they simply add up, and the effect is thus the same. Notice that the electric field at P is not the same in both cases. Here there is a strong electric field pointing away from the positive charge. Here the electric field at P is zero, because the electric field is a vector, and so direction must be taken into account. Here we look at the potential due to a dipole. We see that a positive charge creates a positive potential, and a negative charge creates a negative potential. Notice that directly in between at the halfway point, the potential is zero, because the positive potential and negative potential cancel out. This also gives us another way of picturing potential. We can draw an analogy between potential and height. Positive potential is positive height, negative potential is negative height. Let us now look for the relationship between potential and electric field. We first start with a relationship that we learned from our earlier mechanics course. If we have a potential energy, we can find an associated conservative force. They are related by the negative derivative of the potential energy. But in this case, we know that the force is caused by electric field. And the potential energy can be related to the potential. Both sides have the presence of this test charge Q, but since that's a constant, we can eliminate that, and we arrive at this. The electric field is related to the derivative of the potential. Since the electric field is a vector, we see that the x component of the electric field is related to the negative x derivative of the potential. And even though we haven't shown it here, similarly, the y component of the electric field is related to the negative y derivative of the potential, and so forth. To introduce slightly more advanced notation, we usually condense all that information into saying the force vector is the negative gradient of the potential energy, and similarly the electric field vector is the negative gradient of the potential. You can skip this slide if you want. It's simply a little elaboration on what we mean by the gradient, which involves partial derivatives. In this course, we will mostly focus on this version of the relationship. And notice these two important points. One is that the electric field points in the direction of decreasing potential. The second is that as long as there is a potential difference, there is an electric field. So if as you move your position, there is a change in your potential, there will be a corresponding electric field. Let's get a pictorial idea of what this means. If we have a dipole and look at the potential as we move along the x-axis, we notice that at the midpoint, the potential is zero, but the electric field most definitely is not. The electric field is strong here. And indeed, what is not zero at this point? The slope of the line. So we can think of it this way, that the electric field is the negative slope of the potential. At this point, the height of the graph is zero, but its slope is not. So the potential is zero, but the electric field is not. Similarly, between two positive charges, we see that the slope is zero in between, but the height is not. Let us introduce the concept of contour maps. Here is a temperature map of the United States. Temperature is a scalar, so what are all these lines? They're certainly not flow lines. Instead, we see that these are contour lines. They connect places that have the same temperature. Notice that each line has a number associated with it. So all these places have a temperature of 25 degrees Fahrenheit. All these places have a temperature of 30 degrees Fahrenheit, and so on. Here's another example. This map shows the elevation of the water table. All these places have an elevation of 970. All these places have an elevation of 960. Similarly, we introduced the concept of equipotentials. Here, the lines connect points that have the same potential. All these points have a potential of negative 2 volts, and these have a potential of negative 5, and so on. Now, as you might guess, since negative potential is caused by negative charges, and the potential gets stronger in magnitude as you get closer to the charge, there are two negative point charges here. Here are the equipotentials for a dipole. For a single point charge, the equipotentials would be circles, but here we can see that the presence of another point charge has distorted those circles. We notice that in between, at the midpoint, the potential we know will be 0, and we see that even if we move along the perpendicular bisector, since our distance from each of the point charges is the same, the potential continues to cancel out. And so the potential is 0 all along this line. Let's look at another way of showing the relationship between potential and electric field. In this case, the relation is between contour lines and flow lines. These dashed lines are the contour lines connecting, in this example, places that have equal water table elevation. These are the flow lines showing how the groundwater is going to flow. Let us notice a couple of details. Here, the water flows from higher elevation to lower elevation, and the flow lines are always perpendicular to the contour lines. Here is another example of contour lines and flow lines. Once again, if you look closely, you will see that the flow lines go from higher values to lower values. And we also see that the flow lines are always perpendicular to the contour lines. Let us return to our example with the equipotentials. Here we see that the flow lines, of course, are the field lines. And so the field lines are indeed always perpendicular to the equipotentials. And they are flowing to places of lower or negative potential. Let's look at a few more examples. In this case, a point charge. Here the equipotentials are circles, and the field lines go radially outward, and once again we see the intersection is perpendicular. This is a positive point charge, and so the field lines go away from it, that is, away from high potential towards lower potential. You can see that they are crossing the 70 volt, 50 volt, and 30 volt equipotentials. Also notice something else. The equipotentials are not equally spaced. The spacing is changing. What does the spacing reflect? Well, if the equipotentials are close to each other, this indicates that the potential is changing quickly in a region. If you think of it in terms of the contour lines on a height map, you are changing height quickly, and so the slope is large. Here, if you are changing potential quickly, it means the electric field is large. So, the closer the equipotentials are, the stronger the field is in that region. Here is the example of a dipole. We notice a few points. Here along the perpendicular bisector is the zero potential line going all the way out to infinity. We see again that the equipotentials are not evenly spaced, and we notice that the circles distort as they start feeling the influence of the other charge. And again, we notice that the flow lines or the field lines always go perpendicular to the equipotentials, and that the field lines flow from higher potentials, positive potentials, to 0 to negative potentials. And finally, here's an example with two equal positive charges. Notice the peculiar little x in the middle, where we know that the field is 0. Also notice another point. The field is not constant at different points along an equipotential. For example, along this equipotential, we notice that the field is quite weak over here, but quite strong over here. As before, we note that the field strength is related to the spacing of the equipotentials. On this side, the spacing gets larger and so the field is weaker. But on this side, the spacing gets smaller and so the field is stronger. One more example. Here we have a positive point charge and a neutral metallic object which has been polarized by the positive charge. Notice how the contour lines are circles close to the point charge, but get distorted by the presence of other charges, whether induced or otherwise. Overall, this system is positive, and so as we get further away, the roughly circular appearance is restored. Finally, what if we have a uniform electric field? Well, since that perpendicular relation must hold, our equipotentials are simply straight lines. And once again, we notice that the field flows from higher potentials to lower potentials. So here are some more properties of potential. Equipotentials are surfaces of constant potential. The electric field flows from higher potential to lower potential. Electric field lines are always perpendicular to the equipotentials. And the more closely the equipotentials are spaced, the stronger the field strength, because the potential is changing more rapidly in those regions. And since the field is related to the derivative of the potential, the quicker the change, the stronger the field. We have seen how, given the potential, we can take its negative derivative and get the field. But what if we want to go the other way? We start again with a relationship from our earlier course, which is the relationship between work and force. We know, however, that for a conservative force, the work can be related to negative delta U. And in this case, we know that potential energy can be related to potential. We pull out the point charge Q. And electric field and electric force can be related. And we pull out the point charge Q. And so finally, we have this other relationship between electric potential and electric field. The integral, or rather the negative integral of the electric field, gives us the change in potential. Notice that we are integrating from point A to point B along some path, with dl being the path length element, and we are doing the difference potential at B minus potential at A. In particular, we can set one of these points to be infinity. We usually say that the potential at infinity is 0, so this gives us a way to define the potential at B. It is the negative integral from infinity to the point B of the electric field along a path. Here we summarize the relationship between E and V. Let's clarify a few points to make sure people aren't confused about the relationship between E and V. the slide title says the question. If E is 0, does that mean V is 0? And what about the other way? Here is an example where the potential is 0 at a point, but the field is not. This point is equidistant from the two opposite charges, and so the positive potential created by plus Q and the negative potential created by minus Q cancel out. But the fields, in fact, point in the same direction, and so they add up and become a stronger field in the middle. Here is another depiction of that. Again, note that the positive charge creates a positive potential, negative charge creates a negative potential. And while the potential at the midpoint is 0, the slope most definitely is not. In fact, it is steepest there. If we look at two positive point charges, the potential is not 0, but the electric field is 0 at the center. Here, the two field vectors point in opposite directions and cancel out, but the potentials, both being positive, add up and are strong in the center. They are not the strongest, however, because you can get higher potentials simply by moving closer to one of the charges. We see that in this diagram. Near the 2-point charges, the potential goes extremely high, but in between we can see that the potential is quite high and non-zero here, but the slope is 0, just like the electric field is 0. Here we look at a charged shell. So we just have a spherical shell of charge plus Q, and we look at the electric field and the potential. When we studied Gauss's law, we found that the electric field outside the charged shell behaved like the electric field due to a point charge. And we found that inside the charged shell, the electric field was 0 everywhere. We find similarly that outside the charged shell, the potential looks like the potential of a point charge. And then this is interesting. Inside, the potential is not 0, but is constant. This makes sense. After all, what is the electric field but the negative slope of the potential? If the slope is 0, that does not mean the potential is 0. It simply means the potential is constant. And that is what we see. So remember, if there is a potential difference, there is always an electric field. And if the electric field is 0, it does not mean the potential is 0. It simply means the potential is constant. This teaches us that conductors, since in electrostatic situations the conductors have an electric field of 0, they must also have constant potential, which is why we say that conductors are equipotential surfaces. Finally, let's look at some of the distinctions between potential energy and potential and how they relate to force. Here we look at the equipotentials of a point charge. As we have seen before, they are circles. We can see the field lines pointing radially outward, and we see that the equipotentials are closer together near the point charge and get spaced further out as we go further away, which makes sense because the field is stronger near the point charge and gets weaker as we move further away. Let us now bring in a test charge. This test charge is right now on the 1.5 volt equipotential. Using U equals VQ, we can find the potential energy. The test charge is plus 2 coulombs, and the potential is 1.5 volts. which gives us potential energy of 3 joules. However, we know that if we release this test charge from rest, it will want to decrease its potential energy. So which way will it move? Since its potential energy is positive and it wants to decrease it, it will want it to become less positive. So the positive charge here moves to a region of less potential. It moves outward to this point, which is at a potential of 1 volt. And so its potential decreases, and so does the potential energy. The potential energy goes from 3 joules to 2 joules. Notice that this makes sense in terms of forces as well, because the two positive charges repel. In moving from higher potential to lower potential, the positive charge is experiencing a force in the direction of the electric field, which also flows from higher potential to lower potential. Similarly, if we look at a negative test charge, which is currently, again, on the 1.5 volt line, again, using U equals VQ, we see that we have -2 and 1.5. The potential energy is -3 joules. Releasing this charge, it wants its potential energy to decrease. In this case, that means its potential energy should become more negative. And to do that, this charge must move to higher potential. As it does so, the potential energy goes from -3 to -4. So we see that if we release a negative test charge, it still moves to lower potential energy, but it moves to higher potential. In terms of forces, this again makes sense because opposite charges attract. And in terms of forces, we also see that this makes sense because the force on the negative test charge is in the direction of increasing potential, that is, against the flow of the electric field. Finally, we look at another expression for the work done by the electric field. We have seen that the work done by the electric field is negative delta U, but now we can use U equals VQ to write this as negative Q delta V. And so this is the work done by the electric field on a test charge Q that is moved from V initial to V final. Negative Q delta V is the work done by the electric field. Finally, here are some examples. We have configuration 1. Q1 is 12 nanocoulombs, Q2 is -80 nanocoulombs, D is 6 nanometers, and we move charge Q2 through some unknown path to this position, where the distance is 2D. The question is, what is the work done by the electric field? Pause the video and try and figure it out yourself. We now move on to the answer. V initial is the potential created by Q1 at the position of Q2, and that is KQ1 over D. V final is KQ1 over 2D. Delta V, which is V final minus V initial, is minus KQ1 over 2D. And therefore, the work done by the electric field as we move the charge Q2 through a potential difference delta V is minus Q2 delta V, which simplifies to this. Plugging in numbers, we see that the work done is negative. This makes sense because the charges having opposite signs attract, but we are increasing the separation. So the force from the electric field and the rough direction of motion are in opposite directions. And so the work done by the electric field is negative. Finally, what about the potential created by a continuous charge distribution? As before, we chop up a continuous charge distribution into many tiny pieces each of which can be treated as a point charge. Since we know the potential due to a point charge, we adapt that to dV is equal to k dq over r. Each little charge dq creates a little potential dV, and we add them all up. This integral is a lot simpler than the electric field integral because potential is a scalar. Final example to close us out. We are looking for the potential created by this charged rod, which has a charge density lambda, and we are trying to find the potential at this point P. We first relate dq to lambda. We find the r vector and then take its magnitude. Then we simply plug all that into dV equals k dq over r and integrate. That's the end of this video. I'll see you in the next.